Hey everyone, we have Hélène Esnault talking about restriction math and cohomology.
Thank you very much. Pleasure to give a lecture in your seminar. It's also a little bit intimidating because the founder of the theory is sitting here, and technically I have a program, but technically I cannot really perform it, so it's intimidating. So the talk I will say where the problem is coming from. It's a problem due to Alexander Grothendieck, and why it might be useful so in other circumstances, just as a word. Then I will give a warning why it's what you think might work for his problem does not. Then I will extract from this general problem completely algebraic problem. The problem of Grothendieck is anchored in Hodge theory. I will extract an algebraic part of it. Then I will go mod P, and then I will go p-adically. And then I will say what the p-adic theory is yielding for us, and in particular not yielding for us. So I hope it's, so that's a panorama here. So the problem which has been posed by Grothendieck, and in fact it's a conjecture, but I call it a problem here, is like this. So we do complex geometry. So we have X smooth projective over the field of complex numbers. And then, as we know, it's p-adically cohomology, so sort of as an analytic space here, is p-adically cohomology is endowed with a Hodge structure. And then Grothendieck was considering sub-Hodge structure. So we can consider the problem for Z and for Q, and we will see that ultimately for the corner piece of the problem we are looking at, it does not matter, but let us write here. We can consider a sub-Hodge structure. And a sub-Hodge structure, so we know that one of the gradients of the manifold data of a Hodge structure, that's Hodge numbers. So we can consider the Hodge numbers of the sub-Hodge structures. So in particular, we have those ones. And if we take the C here, which is optimal on the left so that it's not zero, so take the last C, such that it's this subgroup here is not zero, subvector space. Then the prediction is that, so that is a prediction, that there is a sub-variety, sub-scheme, I mean a union of sub-varieties here, with which has codimension C+1, with the property that the reflection homomorphism kills this sub-Hodge structure. So such that if we look at the restriction homomorphism, let me write just no coefficients here, just for HI, and we restrict here to HI x minus Z. Then it kills this sub-Hodge structure. So of course it's a very, I mean, it's an extremely deep conjecture. In particular, for example, it contains a classical Hodge conjecture. And well, for Q coefficients. Now there is one case there is, maybe I should say one more, it contains the classical Hodge conjecture, because if you take the Ci, which is even, and the C, which is just half of I, and so this is a sub-Hodge structure, and that should die on a codimension I cycle, outside of a codimension I cycle. So there is one case where this, so this, of course, in order to understand this, which nobody understands, one has to understand what is a Hodge structure. But there is one case where one does not have to understand the Hodge structure. This is a case where we can take, so let me give two cases. The first one, which is slightly more general, this is a case where the sub-Hodge structure is a whole Hodge structure, but the corner piece dies. And here I say, this is the last piece, I'm sorry, which is 0. The first piece, which is 0. So I want this to be 0. I apologize. So last is the first. And of course, if I look right, it doesn't really matter. And then, so Grothendieck is predicting that there is, so there should be an open. I mean, a codimension 1 subvariety, which just means the complement is going to be an open. There should be an open U, which kills the cohomology. And of course, we can always assume that U is affine, because if we have one U, and I mean, if by accident there was one U which would do it, then an affine U would do it. So let me just write here affine, because that's going to be the general case. Okay? And now notice that here for this this extraction of sub-conjecture of the general conjecture, it is completely irrelevant whether we take Z or Q, because we have the theorem of Vojevodsky, which, thanks to the beautiful observation of Spencer Bloch, implies that the torsion in cohomology is supported in codimension 1. So torsion in HIXZ dies on some U. So it's completely irrelevant. But the moment it is irrelevant, then we are really in extremely good shape, because we know by the comparison isomorphism that this Betti cohomology we were considering here is computed by the Rham cohomology. So we pass to the Rham cohomology. And then Grothendieck, let me just write like this, Grothendieck generalized Hodge conjecture predicts in the Rham cohomology the existence of a U, which is of course dense, which is not empty, which kills the cohomology here. Under the assumption that the corner piece of the F iteration dies. Is that okay? But this now we know the Rham cohomology is less arithmetic. It's defined over the field of definition of X, which is a field of finite type. And in fact, more, it's defined over the ring of definition of X. So we can take a model of X over spec Z, such that, let's say this is smooth, we can make it smooth, we can assume it's affine, doesn't really matter. And now we can look at what, as usual, we can look at what the problem here says if we go mod P. And then for many P's, or for almost all P, so for me, let me write here like this, for many P's, or almost all p's. And we can try to implement some more modern integral p-adic Hodge theory to try to say something p-adically on Grothendieck's problem. And then integral p-adic theory. And before doing that, let me give you another example where we have, we can also descend to algebraic arithmetic geometry, and not only analytic geometry, I mean Hodge theory. The other example is assume, so the other example, so we make, so to speak, a double assumption, assume that X is a product of two smooth projective varieties, and we assume that Y has no A forms, and B has no B form, and Z, pardon, has no B form. So then when we look at H A of Y, HB of Z, inside of H A plus B equals I of X, then it should be the case that we have a product Zariski open, which gives a cohomology. So this should be. So that should be 0. I'm sorry, on this here. I apologize. Let me write here. Okay. So, and then, so it's sort of doubling the assumption here. Okay. And let me make, before going on, let me make a few comments here. The first comment is that it's really, we know, the only cases where we know the conjecture is for I equals 1 and I equals 2. So let me comment on I equals 1. So we are looking at first the Rham cohomology. So then we assume there are no one forms. So now if we had, we try to make everything as algebraic as possible. So we can say if we don't have any one forms, we don't have any H1O, and then we don't have any Rham cohomology. But this is Hodge duality, this is not algebraic. But because we have hard left shades, then not having one forms implies that we don't have any H1O. So in that case, the whole Rham cohomology dies. So this is purely algebraic. Algebraically, we can conclude that the whole Rham cohomology dies, so there's no issue. There's the second case where we know something, so by the same argument here, we know algebraically that if we assume there are no two forms, then again, algebraically, we won't have any H2O. So then what we want to understand is that the H11 is filled in by algebraic cycles, which is saying that the whole Néron-Séveri fills in H2. And why is that true? This is because of the existence of the exponential sequence and Gaga on peak. So that's already, we need an analytical tool here, and then we can conclude. And you see immediately on this example that if we have a situation where we are in this, if we have a, let's say, surface which does not have any two forms, then the H2 is just a Néron-Séveri. But in the Néron-Séveri, I may have, the Néron-Séveri is not necessarily rank 1, may have a higher rank. And so in particular, it's not the case that any open will do it. Only an open which is small enough. So here, the u which we take here is x minus the support of generators of the Néron-Séveri. So that was the second remark here. And now linked to that, let me make a warning here before proceeding. The sort of most universal example one could think of here before proceeding, which fulfills that 0 omega 2 is 0, is to take, because here we are talking on the size of the U, what kind of U could do Grothendieck? So it's to consider X to be P1 cross P1. And inside of P1 cross P1, there is an affine which is as large as we could think of, which is what? We remove from P1 cross P1 the diagonal. If you do that with a higher genus curve, then curve cross itself minus diagonal is not affine, but this one is affine because it is P1. And these fibers over P1 in A1. So in that sense, it's quite big because it's surjective to P1, but still it is affine. And then clearly the H2 does not die on you because the H2 in whatever cohomology you could think of, the H2 is going to be spanned by the two generators of the Néron-Séveri, and the diagonal 1, 1 fills in only one generator. So a spontaneous guess here would be to say, what kind of U does Grothendieck is to consider the following definition due to Gerd-Faltings. He says that a U here, an affine U, is smaller if it is étal. So there is a torus of the same dimension. And this affine here is not small. Why? Because of those A1s here. So that would mean that A1 maps to GM, to all, after all projections. But this is not possible algebraically because there are only constant units on A1. So this is not small. I mean, this one is not small. And but the warning is that life is not as easy as that, because one can construct examples. So that would be the first proposition here. There are examples of n-request surfaces. So they are not rational. They have the corner piece here equals 0. And with the property that there is, in fact, it's family, but it doesn't really matter. I just write it like this. There are small opens in the sense of factings here with the property. So let's say U, so let's say X, let's say U, with the property that the restriction homomorphism here the image here, not only it's not 0, but the moment it is affine, that means I lose at least one class in the Néron-Séveri, an ample class, but I don't lose anything else. So U is small, and the kernel here has dimension 1. So it's a little bit of a defeat, but this is as it is. So now I can start the lecture. And let me go now mod P. And something annoying is happening already. Because I use the notation which was here. And now I assume, so you have an easy proposition here. We say where it comes from because there is one pattern which is absolutely general. So proposition would be that if we assume, so in the situation here, we had on the board here, we have if, let's say 1, if H0 excess omega I S divided by torsion is 0, then there will be an upon in S, which is dense. Such that for any close point on this open, then we have good reduction, so good reduction. Well, yeah, we had good reduction here. So this was, yeah, I said down, so let's say smooth. So we can go such that for any S here, then when we go, I no longer want the Rham here, I just look at the Rham cohomology. And I look at the mod P fiber here, then there is a US. In fact, any US here, which is affine, in excess kills this map here. And but it's in fact this is if and only if. So vice versa, if there is a dense set of S close point such that this is true, then we have no ice force. So this is very strange because Grothendieck is telling us that we have a sort of like the p-curvature conjecture. The restriction homomorphism in characteristic 0 should be 0 on some good open, if and only if it is true mod P for a dense set of S. We don't need all S. So this is quite bizarre. And the reason for this, so I just illustrate here on proof, but we don't want to dwell on it because this is really well understood in our days. The reason for that is that on some open here, we have best change both for the Rham cohomology and for coherent cohomology. So we are looking at this restriction map here. And because this is affine here, then the Cartier isomorphism is telling us that we can look at the second spectral sequence, conjugate spectral sequence, and the Cartier isomorphism is telling us that it's just, I mean, before it's just going, those are coherent shifts, so local cohomologies, and consequently, this group here, which naturally map to H0, Hi, in fact, it's going to be equal because those shifts are coherent and U is affine. And by now, the precise version of the Cartier isomorphism, this is H0 US omega I. So to kill this map is the same as killing this map, but this map here factors through H0 excess shift Hi. which is, just as we said here, it's a false here. But the assumption is that it is 0. So this gives this map. So there is really, this is very classical here, what is written here. And here it is slightly less classical, but still very classical, because in order to go backwards, we need that this map surjects, and here, so we need in addition, so for 2, so for 1, this is just a manifestation of Cartier, and for 2, we need in addition the linear. So, but still, this is annoying. I mean, the formulation is very bizarre. It doesn't really fit well because it's enough to have a sparse S like that. They just have to be dense. And then Grothendieck is predicting that the restriction homomorphism is 0. And I mean, mathematically, it's not difficult, but this is very bizarre to conceive how it could work. But okay, that's how it is. And now let us go to the Rham cohomology, but p-adically. So let us go to integral p complete, p derived complete, the Rham cohomology, which is the same as crystalline cohomology, and more generally to prismatic cohomology. So again, I'm not really a good technician of prismatic cohomology, but I will tell you now what comes out from a precise consideration of this vanishing here, vanishing of the corner piece of the F iteration on the schemes which are considered when we do this prismatic theory. So the prism in my brain, we will fix A, comma I, the prism, and the one I have in mind, because this is closer to me, is the Q de Rham. And we will always assume that so I is locally principal. We will always assume that I is principal. For example, in this case, so we call it D here. And the D here is a Q analog of P, which is Q to the power P minus 1 divided by Q minus 1. So this is 1 plus Q plus etc. plus Q to the power P minus 1. And this one, because initially we are looking in characteristic 0 at the Rham cohomology. So this algebraic the Rham cohomology. It will map, I mean, on a model, on a good model, it will map to this P derived complete the Rham cohomology. So the prism of importance is this one, ultimately. So we can restrict here to Q equals 1. And then if we restrict to Q equals 1, it maps to ZP comma P, which is a one we know since a longer time. And we are going to do the following thing, which is not completely standard. I mean, this is standard here. So maybe I should start here. No, maybe I do in general. Let me consider, so then once we have the prism, we have the prismatic cohomology. So let me just write it as xi of x over A. But we will, the same way we consider here the Rham cohomology mod P and then mod P square, and then we make it derived complete, we could also consider the prismatic cohomology, mod D square, and so forth. But not D square. We want something which is compatible with this P square, P to the power 3, etc., in order to undo this cohomology here, which a priori is just an I forgot to say what is A, I apologize, what is X here. So the X and the U considers will always be first schemes over A mod I, which are P complete, and which are smooth. So here there is a little annoyance because if we take this prism, this A mod I here is not ZP, but it's ZP adjoint a piece root, primitive piece root of unity. And in fact, in reality, because ultimately I come from characteristic 0, I'm even assuming that X is P complete smooth over ZP. So in fact, over ZP. We could take Roy in here and spare us this stupid discussion. So, but the point is that whether we take X or an affine in X or any open in X, so let me write U in general here, we undo this with, so if delta is really the Rham, this P the Rham, let me write the Rham here. So then I just don't write A for simplicity. This is endowed with a p-adic topology. And now, if we look at this prism here, so I never know how you denote this. This is endowed with a Dn topology. So Dn is a system here. And what is D1? This is D, the generator of the prism, of the ideal of the prism, I apologize. D2 is D times phi of D. And Dn, etc. And Dn is D times phi of D times, etc. Phi n minus 1 of D. Is that okay? So that enables you to, and let us write here the cohomology. So I never know whether I should put that here, left or right, or okay. So U A mod Dn. So A mod Dn being a the derived tensor product with Dn. And we will assume here, which is the case for Q de Rham cohomology, we will assume that A mod I is p torsion free, which is the case here. So maybe I should write it here, A mod I, which is p torsion free. Okay. So this topology here can be inserted. See, we can, so the cohomology is endowed with this topology here, which is compatible via the specialization to Q equals 1, for example, for Q de Rham cohomology, with the p-adic cohomology on de Rham cohomology. It's compatible. And in addition, we have the same extension we have for de Rham cohomology. I mean, it dominates the standard extension in de Rham cohomology, which I'm going to write immediately by looking at the system here. So maybe I just write the result here. I apologize. So we have here this de Rham prismatic cohomology is going to map here to the classical limit over n of the cohomology here. The n. And it's going to receive here an R1 lim of the same HI here. I'm sorry, of the bigger group here, and from it, the dn torsion. Those are topological. So we endowed this group here with this dn-adic topology. And this is a topological sequence. So maybe I'll write here topological sequence. And as we specialize to Q equals 1, we obtain here the Rham cohomology. I mean, the completed Rham cohomology. And which maps here to the limit over n of the Rham cohomology. And now this here, for the Rham cohomology, this is just, maybe I should write U because X we think it's proper, but this is a general consideration here. So let me write here. So UN is just U mod Pn. It's a standard notation here. And here, the kernel here is a R1 lim over n of HI, the Rham, U, Pn. So now, so as I said, this is a topological map from the dn topology to the dn-adic topology to the p-adic topology. And the horizontal presentation here is also topological, but more is true. This quotient here, upstairs and downstairs, just by the very definition of the topology, those quotients here are the separated part. So we have here H, let me write separated delta of U mod A. So let's say I separated. And down we have HI the Rham separated with respect to the topology. I don't write it again. And so this is a separated quotient here. And so the kernel here is a closure of 0. So this one here, let me denote it by H I delta closure of 0 of UA, and the same thing in the Rham cohomology. Okay, so I think I hope the board here is clear. I think I wanted, before presenting the results and the discussion, I wanted to say one more thing. I have to find. Yeah, there's something of interest here. The thing of interest is that here, in this p-adic the Rham complete, so this is really p-adic derived the Rham complete. Then, if it happens, if U is the completion of an algebraic scheme over Zp, it receives the algebraic cohomology. So let me write here the Rham. And in fact, if you happen to have a good completion. The recent prismatic log site of what's their name, Yao and Dao or something like this, two former students of Marquesine, enable you to complete this diagram here by putting something algebraic, which better, by the way, called decompleted cohomology, which is algebraic, which maps to the prismatic homology here, and which maps to the algebraic de Rham homology here. So let me write here, let me write just algebraic here. I mean, there is no big mystery here. This definition here, you take this side, this log prismatic side, or this blah blah, and there is an O of 1 sheaf on it, which corresponds to the divisor at infinity. And then in this prismatic side, you look at the R gamma of this O of 1, and that gives you this cohomology here. So there is no mystery, but I just write it like this. But the thing which is interesting is that the kernel of this, assume, now come back to our program here. Assume you manage to prove some vanishing of the restriction homomorphism here. Then it would be a natural question to ask, what information do you lose as compared to the algebraic de Rham homology, which is the initial question. And it is easy to compute. This is just a formal computation, that the classes here which you lose here are the classes which are strongly p-divisible. And what does that mean, strongly p-divisible? So if they die here, by the very definition, they will be p-divisible. That means I take a class X here, and I will be able to write it as Pn xn for any n. But there will be no relation between the xn. Now, strongly p-divisible here, that means I will be able to write px1, x1 equals px2, and so forth. So it's a difference. And this takes in, this fills in precisely this non-separated part of the cohomology. And the same holds true here. That means when you look at the kernel of the, I don't write it because I'm not going to use it, but I want to give the flavor of what is behind. When you look at the kernel here, those are going to be the classes. I mean, assume you have a good compactification, blah, blah. Then those are going to be the classes here, which are weakly dn divisible. And here, if they die here, they will be strongly dn divisible. Okay, so now once I have said that, I hope it was not too confusing. Let me give you what is possible to compute. So we started at 31. So let me give the results here. So the first theorem with Mark and Sasha is that under our fetish assumption here. So now X, again, the assumption in order to do a prismatic homology, even the Rham homology, I'm assuming is that S is a smooth proper over E mod I and in fact over ZP. Is that okay? And I assume, so maybe I'll write it, X smooth proper. Let me write over ZP for simplicity. And we assume, in addition, that H0 omega I is Z. Then the first conclusion is that the restriction homomorphism from prismatic cohomology to, so for any U in X prime. When I say smooth proper, it's always p-adic complete, I apologize. So this one is p-adic complete. Then the restriction homomorphism in the separated quotient of prismatic cohomology on U. Dies. Always. For any U. Now, so, and the same is true, I mean, prismatic also in the Rham. And in fact, there is a beautiful observation here, which relies on the work of Marquisine together with Farb and Watson, is that at least if P is large enough, then this map is going to be surjective. And as a corollary, if this map is surjective, if you want to prove exactly the same thing down, once you the same statement down for this specific prism, which is the Rham cohomology, follows from the statement on the general, more general prismatic cohomology here. I don't write, we call it the magic lemma, but I don't write it. So this is the first statement here. And the second statement is that in our key example, P1 cross P1 minus diagonal, so I can take the class, let's say L is a class of O, let's say of 1, 0. It's one of the missing classes in the Néron-Séveri. It does not die in prismatic cohomology. So now you can interpret this proposition. So I have, I think I will go through the theorems here because some are unexpected. So you can interpret it as a bad news and a good news. So let us start with the good news, because it was, you remember, we argued that algebraically, this class of course does not die because it survives on this huge U. And so this is a good news because in prismatic cohomology, it survives on this huge U. The bad news is that it doesn't give you a hint of what you could do Grothendieck, not Grothendieck algebraically because it's very ambitious, but at least in this P complete world. Okay? You see, this to say that I mean, those two things together, this is a good news and a bad news because any U will do that. But it's a non-empty information, but any U does it. So suddenly we are facing a different kind of problem, and this pen, this egg here, is coming from this P completion. It kills the algebraicity and then it kills, okay. So I think this is okay. So now once we understood that, in fact, to be honest, so there was an Oberwolfach conference and Peter was eager to see what we were doing. So at that time, the prismatic version was not, I mean, half of the proof was written, but not a complete proof. But the Rham proof was complete. So we finished later on the prismatic proof. Peter told us to look a little bit differently, and that was easier. He was, of course, right. And then I was asking everybody, what is the kernel? So So we prove that, and then of course a very important problem, which is already mentioned on the board here, is to understand whether we do have strongly p-divisible element in the Rham cohomology or strongly dn divisible elements here. Because if we don't, this means that when we compute p-adically like this, we get a lot of information on the initial algebraic problem. So I went around because I could not compute. I tried, I could not, or we could not. And Marco D'Adezio, my former student, together with Daniel Caro, came with the following answer. So his first name is Daniel. So they do. So we are on the Rham world in the Rham world here. So they say. So maybe let me try to see whether I don't forget anything here. 1 second. I apologize. My eyes are really bad, so I have difficulties. Yeah. Well, I don't need the first part here. Let me just write the thing which we are talking about. So if we assume, so we are still in this situation here. If we assume that H1 here, then it kills the restriction homomorphism, then HI de Rham. So we are really in the p-completed de Rham version here. So this is p-complete. Huh? And here for any. And they compute it. So we assume H0 omega is 0, which is our standard, which is Grothendieck's assumption, plus another assumption, of which you might ask, where is that coming from? And then the conclusion is that it kills, at least mod torsion, mod p torsion, it kills the restriction homomorphism. Okay?
I'm confused by this R1 lim I. It's not R1 and then HI minus 1.
No, I love this question because I get it at any. For example, yeah, I won't tell you. But this is because I put the torsion here. The I minus 1 would show up if I was putting UN here. Is that okay? Okay, so, but let us focus on this here. So this is as it is. But of course, it's really not what you want, but it's a non-empty information, is that it's any affine, but then you have this baroque assumption here. Now, you have another, once I have written.
Sorry, is this a purely characteristic P theorem, or do you need the lift?
The X, to me, X, for us, X was over ZP, but I think maybe they do it also if X is only, there is no lift to ZP. So let me put a question mark. I would have to look more carefully. Is that okay? But here, in what I have written here, when you write, because you write the diagram X is defined over CP, but of course this bottom line is defined, if X is defined on A mod I, which here for the Rham is just over FP. But in order to make the comparison here, I need CP, but they don't do any comparison. They are really, it's a crystalline version here. So let me now, because time goes on, and I really want to show you the beauty of the thing here. So there is a remark here, which is a proposition, that because of this diagram I have written, I topologize, so to speak, the cohomology. Then when you write this cohomology here, So let me write just delta for simplicity. Is that okay? And now inside, I have, with our notation, the non-separated part of the cohomology. But now it goes to 0. So I thought maybe you might like it because it's like in the link homology. If you take the link homology, present it as an extension of a discrete part with a continuous part, the product restricted on the continuous part dies. This is precisely what happens here. But now you can look at what corollary it has. The corollary is that if you take this L I had, you remember it was landing in the non-separated part of the cohomology, this class of 1,0 on the example. But now I can take the cup product with itself. But the cup product in algebraic de Rham cohomology, of course, is not 0 in x cross x being P1 cross P1. So if you are in P1 cross P1 times P1 cross P1, you can take L, this line times this line is not 0. I mean, it's purely classical algebraic geometry. But here, it will be 0 in H. Now we are 4 of x cross x. I'm sorry, U cross U. So, and then let me write it. This is what Matt doesn't want me to say, but we write it because this is as it is. That means that when you look, when you try to combine mod P and p-adically, so you look at, let's say, the Rham cohomology in general. I mean, over S, and then you look at the product over P of now let me do just by the Rham, but now the P version, P completed, etc., version, and you look at that here, then you will have plenty of classes here which die here. For example, this is the case here for 4, and here x cross x, and here u cross u. So, because they die even integrally. You cannot even hope, so no hope to consider this whole cohomology. I do the Rham here, so I can take Q, so that means I invert P. Let's just do it like this. And then play with a product on HI de Rham, P, U cross U, and then 1 over P. You cannot. So, end of story. So now let me finish by two theorems. Let me lift the theorem of Daniel and Marco here. Let me lift it to prismatic cohomology. So same assumption here. Implies now something is happening here. And now it's again NEU. So affine, P complete, smooth, etc. We had that a few times, but let me write here. So it's not an integral statement, but it's an integral in P statement. 0. But also, I mean, here I have told you here, this is the example here, but in the other example, this was, I should have written it, maybe I'll write it here. We have this, so that means whenever we take this is an example, but it's more general. We take a product class, it's going to die always in prismatic homology here. All your products are going to die in prismatic homology, so that makes a huge supply of classes which die. But in general, so if you do not have this product situation here, you replace, so to speak, this product situation by this extra assumption on H1, then you have this, and because this is 1 over D, and because of the comparison isomorphism of Bargav and Peter, then you can conclude also that this is true on the rigid analytic fiber for the étale cohomology. With the p coefficients. That's the last word. Thank you very much.
Question?
So how important was it that you use this DN system as opposed to the sort of naive powers of D system?
The proof was like that, so but maybe it's not necessary. And I mean, I can give a hint on the proof, not of this H1 here, but really the this one here, because this is where was this DN should here. And I had given the pattern here based on Cartier isomorphism for the mod P reduction in the Rham cohomology. So you want to do something similar. I mean, of course, you have to go up and so forth, but what you do here, you are looking at the shifts here. In order to obtain this, what you need here, I mean, maybe not you need, but you can hope that if you look at the risky shifts here, they are going to be on small enough, I mean, if you evaluate them on small enough opens, and now in this case, this is really faltings open, small in the sense of faltings, they are going to be embedded in ice forms on this open. And now this is not true. So you are not looking at this, you are looking at this. So then it's going to be, the shift here associated to this one is going to be embedded. The torsion freeness is coming from you, from your article, with BMS, I don't know what. And then it's going to be inside of a product of ice form on X over U over A mod I. And then the Frobenius pullback of this thing, and then the Frobenius pullback of this thing, etc. So many times with dn, so n times like this. So that means you are, at each time you are looking, and why is that? It's because the cohomology does that. So then you are left with comparing the cohomology. So when you go mod D here, and you look at the cohomology shifts, you have the ice differential form. Now you have to do the same thing for the twist, the Frobenius twist of the U. And now if we had D square, we could not separate the two directions. And this is precisely what, so that's my answer. It's not really an answer, but that's why you can do it here. And with the same idea, you could not. This is because when you have this line D, and the Frobenius is shifting to another line, and you use this advantage. That then, when you mod out by the product of this line with this line, this is inside of the mod out by one line and mod out by the other line. Now, if you collapse those two lines, which is precisely what happens with the Rham cohomology, then you just have p square, etc. I don't know how to do that. So you need, our original proof was different, was more difficult than, in fact, was more difficult than this proof here. I don't know whether it's an answer, but it gives a clear-cut reason why we do like that. And this is something I learned from Mark. Mark was always telling me, I was always telling him why prismatic cohomology is fashionable, but why? What does that give? Mark would always answer, it gives a Frobenius action, which you do not have on the Rham cohomology. Of course, you have the Rham cohomology is endowed, I mean, crystalline cohomology is endowed with a Frobenius action, but not on the prism itself. There's no Frobenius action on the P, P. But on the prism for Broikissin, or the one I wrote here, there is an action which is highly non-trivial. And why is that interesting that there is an action which is highly non-trivial? It's because it is moving those lines. And here, this is an example. So, I mean, once I've said that, I think you can write the proof here.
Okay, let's think.